In our last lecture, we talked about mechanical properties, and this time we're going to talk, it's going to be a lot of the same subject matter, but we're going to talk about how to determine those mechanical properties. So this unit is on mechanical testing. So like I said, a lot of review really from 1711 and from the last lecture, but really this is just fundamental stuff. So I don't feel bad covering it more than once. And we'll hit some detail that we may not have gotten to before. All right, so when we talk about tensile testing, there's a pretty popular standard ASTM E8 for tensile testing metallic materials, metals. And I've put a copy of or link to ASTM E8 on the course website. There, there's a link to it inside of your labs, or at least the labs where this is used, and there should be a link on the main course, the module that has this lecture in it. All right, so some of the properties that we're going to determine by doing a tensile test. Some of these should be familiar to you: the modulus of elasticity, the elastic limit. Really, the elastic limit is not typically something that we'll get from a single tensile test. The elastic limit, by definition, is where the material ceases to be elastic, and to do that, you need to load the material and unload it and measure it each time. And that is not what's done in a tensile test, but by finding things like the yield strength in a tensile test, you can determine where the elastic limit would be. Let's see, also the proportional limit. We'll look at that in a little more detail here in a second. The yield strength, the ultimate strength, Young's modulus, which is the modulus of elasticity if we're doing a tensile test. We'll talk about ductility and how to characterize and quantify the ductility of a material, and a little bit about strain hardening. All right, so let's go back and take another look at Young's modulus. That is the modulus of elasticity if we're doing a tension or compression test. And remember, this Young's modulus is, the symbol is a capital E, which I seem to have left off of my drawing here, but it's the symbol for Young's modulus is that capital E. To determine Young's modulus, it is the slope of this elastic region on the stress-strain diagram. All right, so that is the change in stress divided by the change in strain. So that is the slope. A stiffer material will have a higher Young's modulus. Now, I don't think that I talked too much about the units of Young's modulus, but we can figure out what they would be since we know what stress units could be, like PSI or KSI or pascals or megapascals. Then we would be dividing something. Let's just stick with PSI because that's really familiar. We would be dividing something like the stress units like PSI by the units of strain. So what are strain units? Well, they're just one. They are millimeters per millimeter or inch per inch, and those units cancel out, and so we're left with units for Young's modulus, or the modulus of elasticity. We are left with stress units. Okay, so the modulus of elasticity for steel, for example, is going to be a pretty large number. So we're going to have stress values divided by strain values, and these strain values are going to be so tiny that it's going to make this, which is already generally a big number, it's going to make it huge. Okay, so something like, so for steel, metric values would be something like 200 gigapascals. Now, I just said that they might be, that megapascals would be a good unit for stress, and then, but now I'm saying that 200 gigapascals might be a good number for the modulus of elasticity, and I just got through saying that they would be the same, and they are. So really, going from mega to giga just means you're using, there are 1,000. It would be 200,000 megapascals, and that's just an awful lot of zeros to be dealing with. And so we just take off those last three zeros from the 200,000 megapascals and call it 200 gigapascals. Now, when you're doing the math, sometimes it's convenient to get everything into the same unit and then worry about whether it's giga or mega or kilo or whatever when you're done with all of the calculations. Same with the inch values. If we had KSI units, a typical Young's modulus measurement for steel might be something like 30,000 KSI or 30 million PSI. All right, so they're going to be relatively large numbers for the for Young's modulus. In fact, the slope on this graph is really exaggerated. Generally, it's very stiff. It's very nearly vertical line when you start off. All right, so you should be able with the data set to look at the data, and what you'll need to do is put this into Excel at some point. We'll do this for a lab, and you'll see the data, and you'll see where you can get good values for stress and good values for strain. And like I said, there are different ways of determining to actually do this calculation. You know, you could find 2 points on here if you wanted to, or if everything is properly calibrated, you could use 0, 0 as one of your points and just find any arbitrary stress and any arbitrary or corresponding strain value and just divide those two, any data point on here. But what's generally done is a linear regression on this section in here, where you have a lot of data points that are good and nicely combined together. And in fact, you'll do that in the lab, as you'll have some software that will do that linear regression for you. If you're not sure what that is, an easy way to get introduced to that is to just play with the trend line tool in Excel. Or better yet, look up some simple linear regression videos and understand how linear regression works. We're not going to go there in this class. All right, now the proportional limit is a spot that is on this graph, and it is the place where this elastic straight line, where there's a very proportional relationship, a nice linear relationship between stress and strain, where that comes to an end. That is the proportional limit. And like I said, all three things are really happening here. The material is starting to yield. The material is ceasing to be elastic at this point. It is beginning to flow plastically. So these are just different ways of looking at more or less what's going on at the same point. All right, now the yield strength, since this, by looking at this graph, it's kind of, and in fact looking at a real graph, it's even a little bit more ambiguous where the actual yield point is. But there's a nice sort of analytical trick that we can use here, and if we just kind of standardize on this trick, then we can get really nice consistent yield point measurements and observations. All right, so this is how this works. First of all, we would measure the modulus of elasticity. That is, we would find the slope of this line. Okay, and you remember back in early algebra days, you had like y equals mx plus b. So m here was the slope, and instead of using y, we're just going to call this axis little sigma. Okay, so we have stress is equal to, instead of saying m, we'll just say E, or Young's modulus, times x, and for x we have strain values, plus b. All right, and we already said that this just goes down to 0, so this really just disappears. So this is a good way of understanding this nice linear portion of the graph, this elastic region. It could be defined with this equation. Okay, so if all we would need to be able to plot an equivalent sort of model of this material in, say, Excel would be to, if we already knew Young's modulus, is to just plug in this equation. Okay, and that would model this part of that graph for us. All right, now to find the 0.2% offset yield, we need a line that is parallel to this line, but we need it to be shifted over 0.2%. And if we draw this line, where that line crosses the stress strain curve is going to be our 0.2% offset yield. Now, everything beyond where this is nice and linear has to come from empirical data. We have to actually get points for all of this to measure this. But we find Young's modulus. That allows us to draw a line along here that will model and follow those data points in the elastic region. And then we offset that line with this strain line, which would follow this equation. Okay, so where does this come from? Well, this is the same as this up here, except we have shifted it to the right. So if you remember doing linear transforms, this will shift the graph to the right by 0.2%. So 0.2% per cent means per 100, or divide by 100. So this is 0.2 divided by 100. That means we just shift the decimal place over 10, 100. We shift the decimal place over 2 places. Okay, so that will give us this new line, and this will be modeled in software. Okay, or you could do this graphically if you had a nice printout of this. All right, so you model this line in the software, and where it intersects the empirical data from the rest of this test, that is on this axis, the stress axis. That is where the 0.2% offset yield is. So notice this is a stress value. When you see offset strength, you're going to get numbers in PSI or KSI or megapascals. They will be stress units because they are a stress. One other thing I noticed earlier I did not put on here is the ultimate tensile strength, or the ultimate tensile stress, which is the measure of strength, and that is where this graph peaks out. So I didn't do a separate illustration of that. I replaced some illustrations and I forgot to put it back in. Anyway, that's where it is. That is the ultimate tensile strength, and that is going to be a place on this axis. So it's a stress or a strength. Also, what's not in these slides is a picture of the upper and lower yield point. I'm not going to redo that because that is in the first lecture in this series. So some materials exhibit that upper and lower yield point, and they exhibit yield point elongation. All right, now we'll talk about ductility. Ductile materials are ones that can flow under tensile forces. So remember ductility and malleability. So malleability is the ability to flow under compressive forces, but ductility is the ability of a material to flow. So we can measure this by doing a tensile test, but in manufacturing, a lot of times we see ductility in operations such as bending. So we bend a piece of sheet metal or a piece of wire. We are using the ductility of that material. So if we have a material that does not have much ductility, we're not going to be able to bend it without breaking that material. So if a material is ductile, that means it can flow nicely. So there are a lot of processes that require this, like extrusion and bending, things like that. So we want to determine the ductility of a material. These are some good ways of doing that. The first one is to find the percent elongation. So when we do a tensile test, we start by putting 2 marks on that specimen, and those marks are separated by a length that is the gauge length. So they are like 2.00 inches apart. We actually physically mark those on the specimen, and then this is generally where we'll attach our extensometer as we do the tensile test, and we pull this thing apart. And then once the piece is completely broken, we'll take the 2 halves of the broken specimen out of the machine and we'll put them back together. And then we'll measure that final length. So this length is going to be longer than the gauge length. Now that is unless we have a very, very brittle material that doesn't flow at all, in which case they'll be basically equal to each other. All right, but if we have a nice ductile material, this will be hopefully significantly longer than it was originally. So how do we quantify that as a percent? Well, first we take this, which is the change of length. So this is L1, that's our final length. Subtract from that our original length, so that is the change of length. This is how much longer the specimen was when we finished than when we started. And we divide that by, we compare that to the original length, and that will give us some number. Well, let's just do an example. Okay, so let's say that we have a specimen with a 2-inch gauge length, and when we're done, it winds up being 2.1 inches long. All right, so that would be 2.1 minus a 2 would mean that we'd have 0.1 inches would be the change in length. And then we divide that by the original length, which would have been 2 inches. That gives us 0.05. All right, so that is, we'll multiply that times 100 to convert it to percent. So that's 5. 5% is the elongation of that percent of that particular sample. Okay, another measure, and I will just say, I've already mentioned it, but an indicator of a material is the fact that you can see this thing neck down and you get this nice cup and cone fracture. All right, the other way to characterize a material's ductility is to talk about the reduction in area. Okay, so which is a very similar formula, except here we have the original length or the original area first. So we measure the cross-sectional area before we run the test. That's going to be a larger number. And then we subtract from that the area after the test and divide by the original area, multiply that by 100, and that will give us our percent reduction in area. So the first one is elongation, so we're talking about the thing getting larger. Here we're talking about the reduction, the thing is getting smaller. So those two values are used a lot to talk about the ductility of a material. All right, so let's look a little bit more at the details of doing a tensile test. Let's see, we already talked about the fact that there is a standard for doing this. It's not the only standard, in fact, but it's a good general purpose standard. All right, I'll say that. We need to have a specimen. We've talked about some of these specimens. They can be different shapes. They can be round, rectangular. They can be actual pieces of material, like a piece of hose or something like that. Then we have to have some kind of way to grip the material, and a way to measure the strain. So a typical tool to measure the strain in a setup like this is with an extensometer. So we actually put a device on here and measure these parts as they move apart from each other. We talked about what the gauge length is and the cross-sectional area of the specimen. And we also said in the last lecture that we're talking about engineering stress, engineering strain. So we are not remeasuring that cross-sectional area. The only time we would remeasure that cross-sectional area would be in this case if we're trying to determine the reduction in area. We wave our hand at any reduction in area as we do the tensile test, so we're dealing with engineering stress and not true stress. All right, I think we've beaten that to death. I think I've talked about most of this, except I haven't talked about like what you would get, what a stress strain diagram would look like for things like an elastomer. So this is a very long, stretchy material, and we'll get a very long, drawn out, very low along the stress strain diagram line. If we looked at glass or ceramic or concrete, if we look at glass, so glass, you may not think about it, but it's only going to deform elastically. At room temperature, if you had something like a glass phone protector, you might have used these screen protectors that are really thin, but they're made out of glass. Those are flexible. You can bend those pretty easily, but they will bend right back to their original shape. They will rebound back to their original shape. They're not going to be permanently deformed. If you try to permanently deform them and you try to bend it in half, it's just going to break. So glass only exhibits this nice linear behavior, and this is also where you can kind of see how brittle glass is, because there's really not much area under this curve. Now, I included concrete here, but normally you don't talk about testing tensile testing concrete. Normally you do compression testing of concrete, and so you do get this little elastic region in concrete, and then as it begins to crush, it will form this kind of parabolic stress strain curve. All right, I put some videos in here of some tension tests. These are in the lecture, or in the lecture notes. Links out to them in the lecture notes, so be sure that you go through the lecture notes and watch some of these. This is a bar of ASTM A36. This is a nice garden variety steel, and if you've never seen steel stretch before, this is a real good video of watching that material stretch. And in fact, if you scrub the timeline after you see it start to stretch, it's really amazing how much this material can flow as it's being pulled apart. All right, so you should be able to look at these two specimens here and determine which one is a ductile material and which one is a brittle material. Okay, so this is the ductile material. We see this this necking, this elongation happening in this material. Over here, this is a brittle fracture. You see it's very straight along the sides, and if you were to measure the percent reduction in area, there really wouldn't be any. Okay, the percent elongation would be near zero on a material like this. We call this brittle fracture. Okay, so setting up a tensile test, you've got your test piece, and this needs to be machined from the material that's going to be tested. The machine needs to be calibrated. Okay, this is just like any other measuring instrument. If you're getting numbers out of this machine, and you're making design decisions out of them and decisions about whether or not to put a material into service, so you need to have reliable data. So when the machine says it's pulling with a force of 1,000 pounds, you need to know that that is accurate. All right, so some testing considerations. The speed can be a factor. So how quickly you apply this strain, you start pulling the parts apart, can make a difference. Okay, so the strain rate and or the stress rate is going to be limited by the standard that you're testing to. This ASTM E8 limits the stress rate. Okay, and its limit, the max, is 100 KSI per minute. All right, and there are other ways of limiting and controlling that speed. Also, temperature is a factor, and the alignment and proper gripping is a factor. If you get the part in there misaligned, you might get a reading that indicates that the part is either stronger or not as strong as it truly is. So you want to make sure that everything is set up properly. All right, this is a really good, this YouTube channel, I highly recommend that you check them out. They've got a series. I've linked out in several of these slides to some of their videos. For instance, this one on tensile testing. Really excellent videos. There's a lot of work in their videos, so I've linked out to them in the slides. This is a tensile test on a polymer. Okay, this is polyethylene. We'll talk about polymers in more depth later on. It might surprise you how much this thing stretches out if you're used to watching metal stress strain test or tensile test. All right, so compression testing is basically the opposite of this. So we're applying a force, pushing force, compressive force, and so compression is more of a factor in certain applications than others. Okay, so you may have heard things like the fact that concrete does very well in compression, but it does very poorly in tension, and that's why we use steel reinforced concrete and pre-stressed concrete to get that concrete such that it's loaded in compression and not in tension. So even when you have a beam where it looks like the top might be in, or the bottom might be in tension, it is actually loaded such that it's always in compression. Some metals, especially when we start talking about tooling. All right, so compressive strength in tooling, tool steels and things like that, really a big factor. Ceramics, obviously, these are used in construction along with concrete, things like that. Put concrete in here under ceramics, but in certain applications, ceramics tend to do really well in compression. Also, you'll see on the sides of a lot of cardboard boxes that they are rated for a certain compressive load along the edge. So they have this edge crush strength, and that's so that you'll be able to determine how high you can stack boxes made out of that particular corrugated cardboard. So in fact, a lot of times you'll see this on here, the edge crush test, 32 pounds per linear inch along the edge of that cardboard. All right, so there are different ways that materials will behave as they're being compressed. So these different modes of deformation and compression. So buckling, shear, double barreling, uniform compression, and this compressive instability or work softening. And then there's also this. So I just this is on the hydraulic press channel. There, so really nice explosive failure there. And really, this is why you wear safety glasses anytime you're working around a press of any kind. All right, tool steels, you'll very often see they will have a compressive strength listed in the specs for that steel. Okay, so here you can see for a particular hardness value, and we haven't talked too much about hardness yet, that you can expect to get a certain amount of compressive strength out of that material. Because a lot of tool steels are designed to work in compressive strength. So think about things like punches and dies. These things experience really extreme compressive strengths or compressive loads. All right, so speaking of tool steels, this is a pretty good example of of what happens and why you heat treat, and sort of the different ways in this case, that the same material will behave depending on how it's been heat treated. All right, so these were both subjected to compressive loads, and both of them failed. They are both made out of O1 tool steel, so the same basic alloy. This one was annealed. This is a dead soft piece of O1, and I was trying to do something with this, and actually it wound up cold heading the end of this piece of steel. So this material at the end here flowed and formed this head on the piece of steel. This other piece of O1 failed under compression, and it just shattered. Okay, this one was heat treated and it was not tempered properly, so this was too hard, and it did not have the necessary ductility. So both of these, both the same alloy, heat treated differently to get different mechanical properties, and as you can see, they failed in completely different ways. It means they're going to behave in completely different ways. All right, so beyond that, I put in some other videos of some compression tests of various materials. So I would suggest that you watch some of those. That one's pretty interesting. In fact, we used to do a manufacturing process to bead. If you ever see a piece of like fuel line or air conditioner line that has a bead on the end, that gets done by holding the end of that tube and then compressing it, and this bead will bump out and form. This one's just showing kind of the natural tendency of a nice ductile tube to make that bead shape. So pretty interesting little video. So there's several of those there. All right, now hardness. So speaking of hardness, I was talking about hardness here, where this is a very hard material, this is a very soft material. What happens when we heat treat and change these materials? There's a trade-off between hardness and toughness. So you'll remember that toughness is the area under the stress-strain curve. Right, so if we look at this material has a lot of ductility, has a lot of plastic deformation, so that means that it would take a lot of energy to rupture this material. So this is a very tough material. So what happens when we heat treat a material? Well, it starts to look like this. So when I say heat treat, I mean a hardening heat treating process. So if we harden a piece of O1 tool steel, for example, we'll go from this nice ductile tool steel to something that notice that the yield point has been raised up on this thing, so it's going to be more difficult to get it to flow, to get it to yield at all, and then there'll be less flowing over here. So this will absorb less energy. In fact, this is a little bit generous over here with this plastic region, especially if we have a part that was heat treated poorly, like the one that I did there. So it would have almost no plastic region here, and you'd just be left probably something more like this. Okay, so you have just this elastic region, maybe a tiny bit of plastic deformation, and very little area under the curve. But look at the yield point. So the yield point's raised way up here. So if you tried to indent this material or bend it, it's going to be much stronger. So it has a much higher ultimate strength, but we've given up all of this plastic deformation out here. So this trade-off between the raising up the yield strength or hardening the material, making it harder, and having it a tough material is a big trade-off that you need to keep in mind anytime you're designing anything It has to do with steels, or steels that could be heat treated. And really any kind of manufacturing process, especially dealing with cutting, really it's hard to think of some that do not, where this does not play a part. So understanding what's going on here is very important. I will say one last thing about this little side trail we're going down, is that the modulus of elasticity for this particular steel is going to be the same. So this is going to be unchanged through the heat treating process. They'll have the same slope here, but what we're doing is moving this yield point up and changing the amount of plastic deformation that's available. All right, so another look here, a nice tough material, but not as strong. A stronger, higher tensile strength material, or compressive strength in this case, but not as nearly as much plastic deformation, not nearly as much ductility. So we might say this is tough and this is brittle. This is hard and this is soft. That's a big trade-off. All right, so maybe that sets us up to talk about hardness testing, okay? Because hardness testing is a good way to evaluate what has happened to that yield point without going and actually destroying the part by doing a stress strain or tensile test on it. So we can measure the hardness by simply trying to indent a ball or a piece of diamond into the surface, and from that we can infer a lot of things about the corresponding tensile strength and compressive strength for those metals. We also get an idea of how easy it will, or how hard it will be to machine those metals. All right, so these are some different hardness tests. All of these are indentation hardness testings, and then there are various other ways of testing hardness. A good sort of cheap shop way is a file test, and we'll also use a little handheld hardness tester in the lab, but it will actually be doing a Rockwell test or Burnell test depending on how we set it up. All right, so first of all, Burnell hardness. We take this little ball indenter that's either 5 or 10 millimeter indenter, and we try to push it down into the surface of the metal, or the material. And generally, these are metals. And so to find the Burnell hardness, you'll take that hardness, the load, and take it divided by the surface area of the indentation. So how big an indentation this ball makes compared to how much you pushed in on the material. This is those same people, that Material Science 2000 channel's video on Burnell hardness testing. I would like for you to watch that. In fact, I might, just expect a quiz question or two out of this video, because this is really a good series, and that video in particular. All right, now the Rockwell series of tests are hugely popular, and in the world of tool steel, the Rockwell C scale is pretty much the go-to standard. Okay, so just understand there's not a single Rockwell hardness. Most of the time, if somebody's talking about Rockwell hardness as if there's only one, they're probably talking about C, but not necessarily. So if you're in an industry where you use one of these more than the others, then it might just go without saying, but it should always be included in any documentation. So that would look like this. 60 HRC would be a 60 hardness Rockwell C scale. So the Rockwell test will either use a little carbide ball, or 1/16 inch ball and a 1/8 inch ball, or a diamond tip braille. So the C scale uses the diamond tip braille. Then there is a minor load applied, and then depending on the test itself, a major load. All right, so let me just drop down here. So this is how this test looks across time, okay? So this is the motion of the indenter up and down along this axis, and this is time in this other axis. So we start by bringing the indenter down and applying a preload. Okay, so the indenter is actually shoved into the surface at the beginning of the test, and that preload, like we talked about in the last lecture, kind of mashes down some of the surface asperities and gets some of the elasticity out of the equipment. And then you apply the major load. All right, so the major load being applied, the indenter will start to penetrate down into the material, and then you'll leave it there for a period of time and let it sit, and to make sure that it's gone in far enough. At that point, you'll remove the major load, and you'll be back to the same load that brought you down to this point originally. So you still have the preload applied here, but this is the amount of permanent deformation that was left in the material by the process of measuring the hardness. And I will mention that all of these indentation hardness testers will actually make a mark on the surface, so some more than others. But if you need a material not to have any kind of marks on it, then you cannot do any of these indentation hardness testing processes or methods. There is a little link on here. I think you'll be doing this one in the lab anyway, and so this just goes through how to do the hardness, the Rockwell C-scale hardness test like you'll do in lab. So that'll just sort of an introduction to that. Here again is the Material Science Theater 2000 series of videos on doing a Rockwell test. So very highly recommended that you watch that one. All right, then there is a Vickers test, and this leaves a little smaller mark than a Burnell test. So Burnell can leave a pretty significant mark on the material. So Vickers will be a little bit smaller than that. It uses this little diamond pyramid to do the indentation, and then you measure the size of that indentation, and based on a series of equations you find the hardness there. This is a look at the Vickers procedure. Again, highly recommended. Then there is the Knoop test. So the Knoop can actually be done on a Vickers machine, but this leaves a little tiny mark. Okay, so this can be used for coatings and things like that of how hard the material is. I will mention for other materials, especially non-metallic materials, there are other ways of determining hardness. And talking about hardness, you know, if you try to do a Rockwell C-scale test on a piece of rubber, that's not going to work very well at all. And so there are durometers tests. So there's a Shore durometer test, and these will be graded by letter. So there are different letter durometer scales, just as there are different Rockwell scales. But this video is a pretty good look at to get you sort of an idea of what like a Shore durometer, a Shore A50 would be. Okay, so that's worth being able to be conversational about that. All right, we said that it makes a difference how rapidly you apply these loads, and if we start looking at things like toughness, this starts to make a really big difference, because you can take a very hard material, something like glass, and if everything is done very precisely and carefully, you can get glass to show an extremely high tensile strength. All right, but we both know that the glass is very brittle, and so this gives you sort of the other side of the puzzle. And you could get this too from a stress strain diagram, but this is a way to measure directly the toughness of a material. All right, so some of the there are tension impact tests out there, but we're going to look particularly at these two impact tests, the Sharpie test and the IZOD test. All right, so these use a specimen of the same dimensions. So basically you machine a specimen to an exact size for all of these tests, and then depending on how it's oriented, let me drop down here, whether it's oriented like this as sort of a simply supported beam, and then this is struck in the middle like this. This is a Sharpie test. All right, so this is, you're going to, when I talk about the hammer in just a minute, this is how the specimen would be located in the fixture to be struck. So this is the Sharpie orientation, and this is the IZOD orientation. So it's pretty easy to keep straight. If you remember, this looks like an I, and you can see the little C here for a Sharpie test. All right, so here's how this thing works. Both of these tests work essentially the same way. You have this hammer, and the hammer is mounted on a real nice freely swinging ball bearing. All right, so if we were to allow this hammer to just swing freely, it would move all the way to the other side, and it would be the same height on the other side as it was on this side, neglecting friction, and we're already saying that we can take that out. Then what we can do is dial this in and say that that's the 0 point. Okay, so if we let this swing without striking anything at all, then you see it comes this needle would wind up pointing up here to 0. Okay, now if we when we take a weight and we lift it up, then what have we added to that weight? We've added a certain amount of energy, right? So we have, if this is just sitting here, we've lifted it up and pinned it in place, then there is a known amount of potential energy in this hammerhead. Well, if we let the hammer swing and it strikes, let's say it strikes a very, very brittle material with hardly any strength, any toughness at all, then this hammer would swing almost back up here to 0. Okay, so we would have a very small reading on a brittle material. On the other hand, if, like we've illustrated here, we let it swing and we let it strike a piece of annealed steel, or something like an annealed piece of S7, then that's going to absorb a lot of energy. It takes a lot of energy to break that type of material. And that would wind up with a very high value here, because the needle on this side would not move very far. That means that a lot of energy goes into that specimen. All right, so that's the way this thing works. This is a nice little video of an actual Sharpie test example. And in fact, if this is the one I'm thinking of, they actually show you how to determine the ductile to brittle transition temperature. So let's just see if we can figure out what's going on here. This is an example of a test question. Which material is tougher, sample A or sample B? Okay. Now, don't be fooled by thinking, well, this dial moved up more. Notice as the more the dial moves, the smaller and smaller that number gets. Okay. So this is the tougher material. This material would have absorbed more energy, material B. Now, also be careful the way that the question is worded, because I might say, which one, let's say I might say that 2 pieces of O1 tool steel were heat treated. One was heat treated to become very hard, and one was heat treated to become very soft. Which is the hard one and which is the soft one? Okay, in that case, this is the hard one, because harder materials are going to be less tough, less brittle, all things being equal, than a material that's annealed, which would have a higher amount of toughness, more impact energy. So make sure that you're careful with the wording of the question, and make sure that you're reading those scales properly. Here's again these folks doing a nice Sharpie impact test. Okay, I mentioned earlier about the ductile to brittle transition temperature, and that is if we did a series of impact tests, and we started with a very, very cold specimen, and we did a test on that one, and then we allowed that another specimen to heat up a little bit and did a test on that, and then let it heat up a little bit, and then did a series of tests across various temperatures. Then what we would see is this, in some materials, would start to lose their toughness as they get colder. Okay, so this is a very important factor when you're talking about toughness, understanding whether or not that material exhibits this ductile to brittle transition phenomenon or not. Because here you see much tougher samples at higher temperature, but then you go through this zone here, at this temperature here, it just drops, and we have a much more brittle material as it gets colder. All right, I've included this slide here about shear testing. I'm not going to take shear testing apart too much. You're going to do some shear testing in the lab. This is because it's difficult a lot of times for students to visualize where the cross-sectional area is that's important to the shear test. Okay, so it's going to be the cross-section that fails in the test. So if the test were to be complete, where is the zone where the material failed? Okay, and so that's the best way to think about it, is what would be the cross-sectional area of the material where it would fail if we did a shear test on it. So this is a shear testing apparatus, and you can see that it's designed kind of like a guillotine here, and it pushes back and forth on the two edges of this specimen here. So I just stuck this in here to point out where that cross-sectional area is, because that's one of the most important things when we're talking about shear testing. The other thing is, if we have a stress-strain diagram that comes from a shear test, then that modulus of elasticity region would actually be the modulus of rigidity, or the shear modulus, and instead of being an uppercase E, it would be an uppercase G in most cases. Alright, there's also a video in here about doing a fatigue test. I mentioned that briefly in the last lecture, but I'm going to leave you on this one for you to watch this fatigue test, and you can, again on this one, expect some quiz questions, because I can't do a better treatment of fatigue testing than they do. So definitely expect some quiz questions on this one. I might go into the slides and flag some of these so that you'll know exactly which ones are going to be on the quiz. Alright, but that's all I've got for now, and we will see you next time.